As we have learned from the videos on shrinkage and warpage, all parts shrink and warp. The question you need to answer is it within the part's tolerance? We use deflection plots to see how the part changes in size and shape. It is up to you to determine if the change is shrinkage or warpage. Up until now, we've talked about how you can use deflection plots to identify shrink and warp. Deflection plots, when initially plotted, use best fit to display deflections. This technique makes it appear that the part is shrinking and warping towards its centre. Although this technique is visually appealing, best fit doesn't provide you with a reference for comparing warpage. With best fit, warpage isn't easily quantifiable. Thankfully, by using anchors, you can set up a reference so you can measure the part's warpage accurately and consistently. An anchor can be defined with 1, 2, or 3 nodes. Typically, 3 nodes are used to form an anchor and often called an anchor plane or reference plane. Anchors define 2 things at the same time: a new local coordinate system and constraints based on the local coordinate system. When creating an anchor plane, the first node defines the origin and is completely constrained in translation. The deflection at the first node is always 0. The second node defines the positive x direction and has its translation constrained in the y and z direction. Its x translation is not restricted. This allows the part to shrink in the x direction. The third node establishes the positive y direction and is constrained in z translation. The positive z direction of the anchor plane is also established using the right-hand rule. Now that the anchor plane is created, the deflection result orients itself to the plane based off the constraints of the 3 nodes, which gives you a defined reference to compare deflection to. You can also use the examine tool with nodes to identify their before and after deformation values. When changing between best fit and anchor planes, the distance between part nodes does not change. As the paperclip orients to fit the anchor plane, the nodes move in space, governed by the constrained anchors. This changes their x, y, and z coordinates. But the distance between nodes on the part does not change, as the part isn't changing shape between anchor planes. Now, the remote is measured to determine how far specific nodes have moved from their original locations. Pay specific attention to Z deflection, as this represents the out-of-plane warpage that you're interested in. To appropriately use anchors, you need to understand how warpage is defined for a specific part or feature of a part. You may need to use several anchor planes to comprehend warpage for a particularly complex part. Anchor planes are a useful way of visualizing how a part warps. However, to provide meaningful information, it is important that you understand how to create useful anchor planes and interpret them.